Another example now, a light bulb company finds that 1% of their light bulbs are defective. So in a box of 50 light bulbs, find the probability that we've got no defective ones or the probability that we've got 2 or more defective light bulbs. Now before I start here, just consider your success and your failure. And it doesn't have to be that a word that's negative like defective necessarily means failure. It's up to you how you define it. And I find the simplest way of doing this is to just write out what binomial expansion you're interested in. Now I'm thinking I'll put the thing that I'm interested in first every time. That way I've got a bit of a system. So if I say I've got 1%, I could write it as 1%, or I could write 0.01, and obviously the complement of that is going to be 0.99, and I've got 50 light bulbs. So what you're picturing in your mind here, you're not drawing this, but you're imagining it's either defective or it's not defective. Defective, not defective. And we've got a branch, a tree here that's got 50 different sets of branches. Obviously we don't want to draw it, but that's what we're imagining when we think of this. There's 50 different stages. So now I know that any one term is going to be 50 choose something, 0.01. Now this is my success, which weirdly is how I've chosen to define it. You might do it the other way around, equally fine, as long as you're careful with your language. A defective one is going to be raised to 50 minus r, and a not defective one will be raised to r. So to do part A, I want to find the probability of 0 defects. That means I want this to be raised to the power of nothing. So let 50 minus r equal 0, therefore r equals 50. So I want 50 choose 50, and then I want 0.01, obviously to the power of 0, that's just going to be 1, and in fact 50 choose 50 is also 1. We're effectively wanting the first term of the expansion, which we know is very simple. It's just going to be 0.99 raised to the power of 50. So now putting that into my calculator, I'm going to get 0.99 to the power of 50. It's equal to 0.605 to 3 decimal places. So it's fairly likely then, about a 60% chance, that if I grab a box of 50 light bulbs from this company, probably they're all good to go. 40% chance that there's going to be at least one that's broken. Okay, so for part B, what's the probability of 2 or more defective bulbs? Now, I could say, let's get the probability of 2 defects plus the probability of 3 defects plus the probability of 4, oh gosh, all the way up to 50? That would be crazy, right? So instead, let's consider the complement of that. We know that all of the things that could happen add up to a certainty, which is 1. So if we find the probability that we have 2 or more defects, really we could find that by saying, well, let's do 1 minus the probability of 0 defects minus the probability of 1 defect. And again, a choice in setting out, you could do 1 minus this, minus that, or you could say, let's do 1 minus adding the probability of having no defects or 1 defect. It amounts to the same thing. I'm just going to choose to leave out those extra brackets and subtract each one of them separately. One of them is something I've already found. So I've got 1 minus the chance of no defects at all, which means that the good ones, we had 50 of those. So I can put that working in again, actually just put it into my calculator to keep it in exact form. I'm just going to put it like that because we found that this was 1 and this was 1, so we didn't really need them. And then here, the chance of getting 1 defect, well, I'm going to need 50 choose 49, or you could do 50 choose 1, same thing, it's going to be 50. And then we need to do 1 defect, and the good ones raised to the power of 49, because there's obviously going to be 49 good light bulbs in there. And what I'm going to get is 0.089. Let's go to 3 decimal places again. So there's around about a 9% chance that there's 2 or more broken bulbs in there. Now just always think back, does this kind of make sense? Does it feel sort of right? We've seen that the probability of getting no defects, sorry, that's right, 0 defects, was 0.6. So that means the probability of getting at least 1 defect is going to be around about, let's call this roughly, around about 0.4, okay, because it's that minus that. So then what's the chance of getting exactly one defect? Well, that would be just this part of the calculation here, which is 50 times 0.01 times 0.99 to the power of 49. That gives me 0.305. So this is making a little bit of logical sense now, just checking it sort of feels right. The chance of no defects, pretty good. So out of getting at least one defect, we can see that the most likely thing is that there is exactly one. Getting exactly two would be a little less common than that, and it would get less and less common to have a whole heap of defects. Obviously, there's not many defects. So the chances of getting like all 50 defective would be, astronomically small. So these numbers are going to get small drastically in an experiment like this, but always just make sense of it. And if you prefer to find each probability separately so that you can see that it kind of makes some logical sense, then go ahead and do it, because that will help you spot your mistakes. Another example here, I have a 92% chance of hitting a target. So straight away I'm thinking it looks like this, where this is my success and this is my failure. In 120 attempts, so I need that here, find the probability of exactly 100 successful shots. Well, any one term is going to be 120 choose R, 0.92 to the 120 minus R, 0.08 to the R. So if I want to get exactly 100 successful shots, I want this number to be 100. So clearly R needs to be 20. So I've got 120 choose 20, and again 120 choose 100 would also work. 0.92 to the power of the number of successful shots I want, so that's what I want, and this is what I'm going to get because it's sort of the complementary amount, and into the calculator it goes. And of course, the more attempts you have, the more unlikely any one particular number of successes is going to be, because there's just so much variety, there's so many things that might happen. So any one of them is a very small chance indeed, and in fact this one comes out as 0.0008. Let's go 1 and call that 2 significant figures. And you can see that if you get a really small number here, significant figures almost makes more sense than decimal places. You'll generally be told how to round your answer. If you can express it as a fraction, do so, but really small numbers will get to the point where you can't express them easily as fractions unless you do a whole heap of work calculating this sort of stuff by hand. Okay, now let's look at a harder example. Now this is more difficult because each stage is actually a compound event, so there's a little bit more work to do at the start. Joe makes 20 shirts a day. Now he works a little bit slower than Jenny, who makes 30 shirts a day, but perhaps he's a little bit more careful. Only 2% of his have defects. Jenny makes more shirts, but 4% of hers have defects. If they package a randomly mixed parcel of 30 shirts, find the probability that no more than 2 shirts are defective. That means we want the probability that none of the shirts are defective, plus the probability that 1 is defective, plus the probability that 2 are defective. So in that parcel of 30 shirts, we're okay with 0, 1 or 2 defects, but just no more than that. So I'm sort of thinking ahead, I'm going to have to find 3 probabilities and add them together. But first I need to consider what's the chance of a shirt being defective in the first place, especially when we don't know who made it. Now you can draw up that sort of tree diagram to get your 4 outcomes if you want to, or you could just think it through. We've got to add together the probability that it got to here, Jenny made it and it was defective, with the probability that Joe made it and it was defective. So if Jenny made it, well, Jenny makes 30 out of every 50 shirts. So the chance of Jenny making it is 3/5, and the chance of it being defective is 4%, which is 1 out of 25. So the chance of getting it to here is, what's that, 3 over 125. So we have 3 125ths, plus the chance that Joe made it, well, that's 2/5, and having a defect, 2%, that's 1 out of 50. So we've got there a chance of 2 out of 250, which is 1 out of 125. So we're adding those together, and we can see the chance of a shirt that we just randomly choose when we're not sure who made it is going to be 4 125ths. So now I can take that and look at my whole experiment and say what I've got then when I take 30 shirts is the chance of a defective one is 4 125ths. I could put that first if that's what I'm interested in, plus the complement of that, which is going to be 121 125ths. That's the chance that it's a good shirt, the chance of a defect. And I'm choosing 30 shirts. So any one term is going to be 30 choose something for 125ths to the power of 30 minus that, and 121 125ths to the power of that r. So now let's work over here. We want the probability of 0 defects plus the probability of 1 defect plus the probability of 2 defects, but no more than 2. So if we want no defects at all, we want 30 minus r to be nothing, so we need r to be 30. So we need 30 choose 30, and this term will be just 1, so we need 121 125ths to be raised to the power of 30, so we want all the shirts to be good, plus 30 choose 29, where we have 1 defect, so that's the chance of a defect. We raise that to the power that we want, which is 1, and we raise the other thing to 29, plus 30 choose 28. The chance of a defect, we can have 2 of those, and we can have 28 shirts that are not defective. That's my working. All of that goes into the calculator, and I think we end up with 0.930 to 3 decimal places. So the chances are pretty good that when Joe and Jenny send out a randomly mixed parcel of 30 shirts, it's a 93% chance that there's no more than 2 bad shirts in there.